Hello everyone, welcome to LICD Lecture number 35A. Today we are going to discuss the transfer curve for Opamp in open loop and closed loop configuration. So let us start. Let us consider this circuit diagram over here wherein we have Opamp connected in the open loop configuration. We have applied voltage V1 to the non-inverting terminal. We have applied the voltage V2 to the inverting terminal, and the difference between the two input terminals is called as VID. We have denoted it as VID, input differential voltage. The op-amp is powered with plus VCC and minus VEE power supplies, and the output is measured at pin number 3, which is the Vout terminal. Okay, so here is the description of the open loop operation of the op-amp. So here we have applied the input signals V1 and V2 to the respective non-inverting and inverting input terminals. Now, as we know from prior discussion that the open loop gain of op-amp is very high. In fact, for IC741, the open loop gain is 2 into 10 is to high, 2 into 10 is to 5. Okay, but for ideal op-amp, it goes to infinity, very, very high. So since open loop gain of op-amp is very high, the output voltage of this configuration of this circuit wherein the op-amp is in open loop condition is either a positive saturation or a negative saturation. Okay. Now, when it is a positive saturation, whenever V1 voltage, there is a voltage at the non-inverting terminal, is greater than the voltage at the inverting terminal, that is V2. So whenever voltage V1 is greater than V2, output will be at positive saturation level, that is plus Vsat, and whenever V2 is greater than V1, the output will be at negative saturation, that is minus Vsat. So the resultant transfer curve will look something like this. Okay, so this is the curve for the op-amp in open loop configuration, wherein we have, this is the ideal transfer curve for the op-amp. Okay, so here as we have said already, VID is V1 minus V2, basically the difference. Let me show it to you. Yeah, VID will be V1 minus V2. So we are plotting on the x-axis the differential voltage, the input differential voltage VID, and on the y-axis we are plotting Vout. Okay, so for open loop configuration for ideal op-amp, basically we have this characteristics. Okay, the blue color line you will see over here. And so if whenever VID is greater than 0, that means what? That means voltage V1 is greater than V2. My output of the op-amp is at plus Vsat. And whenever VID is less than 0, that is it is negative, the output of the op-amp stays at minus Vsat, that is negative saturation. And the transition between the positive and the negative saturation is almost like a vertical straight line. Hence, we can say that the slope of this curve, the slope of this transition is infinity because it's a perfect vertical line. Hence, the open loop gain is considered to be infinity for an ideal op-amp. And if we want to divide this into different regions, well, the region to the right of to the right of 0 and to the left of 0, that is positive VID and negative VID, are all saturation regions. And for the linear region, it's basically on the y-axis itself because it's very, very small. So we can say that the op-amp in the open loop hardly behaves in the linear region at all. Okay, so there are some points which we can conclude. So number one point is we can determine the relation between the Vout and VID. So Vout will be equal to AOL times VID, where AOL is the open loop gain of the op-amp. Now, since the value of AOL it's very high, ideally infinity, therefore very small changes in VID, a minute microvolt or a millivolt change in VID will produce either a plus VSAT or a minus VSAT at the output. Now, as we have already discussed before, point number 3, that is whenever VID is greater than 0, output will be at plus VSAT, and whenever VID is less than 0, output will be at negative VSAT. Okay, this is just a confirmation of this behavior. So this entire behavior, where the slope of the transition between minus VSAT to plus VSAT, it's very, very vertical line. Hence, the open loop gain is considered to be infinity. Basically, the slope of a vertical line is infinity. Fine. Now let us see this behavior. So let's build an op-amp. Let us go to the reflection spot. So let's build an op-amp in open loop configuration using 741 IC basically, and let us find out the slope of the transition region. So I'm building this circuit in LT Spice. This is LT Spice free software, EDA tool basically. So here I have taken Opamp as OP07 from the library over here. So here you can type OP07, it will appear. It's a precision operational amplifier, and here we can give the power supply connections VCC and VEE. So we have given over here plus or minus 15, and V2 terminal is grounded, which is connected to the inverting terminal or V minus, and the non-inverting terminal is connected to zero point 0.1 millivolt signal. Okay, basically we are varying the value of V2, right, from minus 5 millivolt to from 5 millivolt to minus 5 millivolt in the steps of zero point 0.1 millivolt, and we are checking how will be the behavior of the output with comparison to the difference input. Okay, so we'll go to simulate, we'll run this, and we will plot the characteristics now. So we'll plot the output curve. So this is my output curve, and on the x-axis we should have V plus minus V minus, correct? So it will be V of V plus minus V of V minus. Okay, so this is my curve. So basically it's quite close to whatever we have studied in the theory, but in theory we have considered the op-amp to be ideal, and here we are using a OP07. As you can see, OP07 op-amp, so it's a practical op-amp, so it will have some slope. As you can see, this blue color line and this orange color line which is coming in the simulation are quite resembling each other. Okay, so this is my saturation region, this is my also again a negative side. This is minus VSAT, this is plus VSAT. Let's check the value of plus minus VSAT. If I take the cursor over here, it's around 14.06 volts plus VSAT, and we have a minus VSAT value of minus 14.06. Okay, that's fine. And if we want to find the slope, we can easily find the slope. Okay, so here let's first check the linear range. So I'll expand this part and let's check. It's starting from 0, and here the value is around close to, it's very close to 100 millivolt. Basically we can see it carefully. It's very close to 100 millivolt. If I properly adjust this over here, as you can see, 100 millivolt. So basically what I am saying is this linear region over here is actually it's almost zero in case of ideal op-amp, but in case of OP07 in open loop configuration, this linear range is around 100 millivolt. Okay, that's the point. And yeah, so if you want to find the slope of this, we can maximize this part, and we can take two coordinates over here. So one coordinate will be over here. Let's consider to be here. Let's say at -3, and another coordinate I'll take over here. Okay. So now we can do x2 minus x1 and y2 minus y1 and calculate the slope. So basically we have the two coordinates over here. So the output, uh, yeah. So let's check that value. So V out upon VID. So the difference between the V out is, it's actually minus of that. So yeah, we can calculate easily. 6.9024 divided by 24.541 microvolt. So the value is coming out to be the number which is coming out to be over here. Let me write the number. This is the slope actually, and the slope will be the open loop gain. Okay, so let me start with the text. So the number which I'm getting over here is AOL is given by slope, which is given by 281,259. So this is the number which we are getting out of simulation. Okay, so basically we got this by dividing this numbers. This is the difference actually. So let me not write that. So let me just write this result over here. Okay, so this is we have found out the slope, and as per this slope we are getting a number which is 281,259. So this is the number which we are getting. Okay, so with LT Spice 281, yeah, we're close to this. So we can see its value is greater than 2 into 10 is to 5, And yeah, this is the slope of the transition region, this transition region, and that is nothing but your open loop gain. So open loop gain of 741, OP07 Opamp is this much, greater than 2 into 10 raised to 5. And its linear range over here, its linear range we have found out to be around 100 millivolt. Yeah, you can check. Yeah, it's around 0.101 millivolt. You can see the x coordinate below. So we can write over here the linear range is 100 microvolt. So these 2 points we have added now. So this is what the result of in Opamp behaves in open loop configuration. We have a very low linear range, 100 microvolt, and the gain open loop gain is 2 into 10 raised to 5, greater than that basically. Okay. Now let's get back to the PDF. Okay, fine. So now let's check the other part, that is the Opamp in the open loop. And here is my practical transfer characteristics. So basically just now we have observed this, correct? Yeah. Okay, let me go back to the diagram. So let's check this value. Let's check this characteristics now in detail slightly. Okay. So this is my practical transfer curve, wherein we are considering the Opamp to be a practical Opamp. So this is my practical transfer curve of Opamp, wherein I have VID will be normally in millivolts, and this is my slope, the transition region. So we have a very, very small linear region. So the slope of this line will be around 2 into 10 raised to 5 for 741 IC. And we have just now evaluated in LT Spice that the slope of this line was around greater than 2 into 10 raised to 5. And whenever VID is greater than the linear range of the Opamp, so it will be in the positive saturation. If it is less than that range, it will be in the negative saturation. So whenever VID is greater than a certain value, it will be positive saturation. Whenever VID is lesser than a certain value, it will be in a negative saturation. In between this two, positive and negative saturation, we have a small linear region. Okay. So in order to draw the practical transfer curve, we consider 741 Opamp. So basically output voltage is given by AOL times VID. So what is the VID given by? V out upon AOL. So let's say that the output voltage is either plus or minus Vsat, right? So assuming that plus or minus Vsat is plus or minus 14 volt, and AOL is the open loop gain of the Opamp is 2 into 10 raised to 5 or 741 IC. We calculate the value of VID, right? It will be a range. So VID will be plus or minus 14 upon 2 into 10 raised to 5, which will be equal to plus or minus 70 microvolt. Actually, this slope is incorrect. The slope will be only for the AOL. So this, kindly ignore this slope part. Okay, the rest all is fine. So what does this VID plus or minus 70 microvolt means? So indirectly, we have to find out the coordinate of this positive and this negative point on the x-axis. So here it is 70 microvolt and here it is minus 70 microvolt. That means the range of this linear region is starting from 70 microvolt plus 70 microvolt, and it's extending to the negative side, that is minus 70 microvolt. So that means what? As long as the difference in the input terminals, that is VID, is in this range, the op-amp will act as a linear amplifier. What do you mean by linear amplifier? The output will be proportional to the input. Any one value of the output and input relation we have, we can find the any other point on the corresponding line, because it will be a straight line in the linear region. Okay, it's a very, very important point. So if a VID, that is the difference between the two inputs, is lesser than around 70 microvolt and minus 70 microvolt, your op-amp will work as a linear amplifier. And whenever VID exceeds the above range, then whatever is the shape of the input signal, output will be a square wave between plus Vsat and minus Vsat, as depicted below. Okay. So to increase the linear range, we need to decrease the value of open loop gain. and this is possible only with the negative feedback. I repeat, to increase this linear range, we have to decrease the value of AOL, that is the open loop gain, and this is only possible with the negative feedback. Okay, now a few pointers before we conclude today, and we have seen this behavior over here. We have seen this behavior in these characteristics. So this is my practical basically this is my practical transfer characteristics, what VID versus output versus VID, and we have seen the linear range over here. The linear range was around 100 microvolt, and the open loop gain is around 2 into 10 is to 5, greater than that, in fact. Okay, but this was OP07. What we have done the analysis was for 741 op amp. Okay, so the transition region will be varied from device to device. Okay, now some notes over here. Output of the voltage amplifier, that is op-amp, cannot be more than the supply voltage. Okay, that means what? Even if you apply some AC input and output is supposed to give you, let's say, greater than the supply voltage, it cannot give that value. Okay, it will saturate. uh, Plus VSAT or minus VSAT. Now next, if the differential input VID is such that AOL into VID is greater than the DC power supply, then the op-amp will enter into saturation region. So that means what? If my differential input is such that it is making this product greater than the power supply, then the op-amp will definitely enter into saturation region, and the output waveform will get clipped to maximum 90% of the supply voltage. Okay, so let's say it was supposed to give you 15, it starts clipping at 14. That's the meaning of it. So this voltage at the output is known as the saturation voltage. So can you see over here these 2 points on the curve? This is my saturation voltage plus VSAT, and this is my negative saturation voltage. We can check its value over here. It's plus VSAT 14.0906, and here it is minus 14.06. Okay, so these are the two saturation voltages. Let's get back to the PDF. Yeah. Now we go for the closed loop configuration. Remember, we have made a statement that to increase the linear range of the amplifier of the op-amp, we need to decrease the value of the open loop gain, and this is possible only with the negative feedback. So what we do is we make an op-amp in a negative, in the closed loop configuration like this. Let me just open the second PDF and show it to you. So I think, yeah, that will do. Yeah. So this is my diagram, that is op-amp in the closed loop configuration. Why it is called as closed loop? Because as you can see, output of the op-amp is connected to the input via resistor RF, which is called as the feedback resistor. And as we know already, we have done a lot of linear circuits in op-amp. So this is nothing but your inverting amplifier. Okay, and the negative feedback is indicated that the RF register is connected to the inverting terminal of the op-amp, input terminal of the op-amp, and the same, the other end of the register is connected to the output. So we have a negative feedback over here. Okay, so the above op-amp over here is in closed loop mode, and no, it's not inverting. It's basically non-inverting amplifier. Why non-inverting amplifier? Because input is applied to the non-inverting terminal. So it's a non-inverting amplifier. Okay, and we have derived it earlier that the output expression for this non-inverting amplifier will be given by 1 plus RF upon R1 into V1, where V1 is the input. So that means the closed loop gain will be V out upon V1, right? So ACL will be given by 1 plus RF upon R1. That will be 1 plus 10K upon 1K. That will be 11. So this is my closed loop gain, and this closed loop gain of 11 is much smaller compared to the open loop gain, that is 2 into 10 is to 5. So definitely it will result in a linear input range increase. Okay, so linear input range is the range of input over which the op-amp works as a linear amplifier. Let's see that range now. Okay, so this will be the practical transfer curve of op-amp in closed loop configuration. As you can see, it is similar to your earlier open loop configuration, but only difference is the slope is quite less. Earlier it was for open loop configuration, this value, the slope was very high, 2 into 10 is to 5. Right now it is just 11. Okay, just 11. And again, we have a quite drastic increase in the linear region. Now we will observe that shortly in the reflection spot. Okay, so let's go to the reflection spot and build a circuit of op-amp in closed loop configuration, and let's find out the closed loop gain and the linear range. Okay, I'll go to the LT-Spice simulation. I'll close this window and I'll open the transfer curve of op-amp in closed loop mode. So this is my op-amp in the closed loop configuration. We have R2 and R1 register. V2 is applied to the non-inverting terminal. So this becomes your non-inverting amplifier configuration. Now let me simulate and run. Okay. So before that, I have to name these terminals as V minus. This will be V minus, and this will be V plus. Okay, we have to subtract them actually. Okay, fine. So now we got the, now we'll simulate it and we'll check its output. And on here, on this side, we have to write over here V plus, V of V plus minus V of V minus. Okay, so that's the curve which we are getting. Fine. So over here, this is my plus VSAT. This is around 14.02, and this is my minus VSAT, which is around minus 14.02. Okay. Now let's check the other parameters over here. Okay, if I don't do this, if I directly plot that, let's wait. I'm directly plotting the input range. So that will give me this plot. Okay, yeah. So this is my transfer curve. My x-axis is my V2 voltage, which is varying over here. Fine. And my y-axis, oh sorry, my y-axis will be my V out. That is VO, correct? And this curve is resembling this. As you can see, the blue color curve on the right hand side is what we have studied, and this orange color curve is what we are getting. Now we have to find out how much is my uh, slope. First of all, how much is my linear region? So let us find that linear region over here. Let me take one cursor and take it over here, and let me take another cursor and bring it over here. Okay, so as you can see very clearly, the linear region has definitely increased. So is this my linear region? Let us cross check it. Yeah. So this is around 2.582. Okay. So linear volts, it is in volts. Huh? So if VID difference is 2.52, the difference between this linear range has drastically increased. Earlier it was in microvolt, now it has gone to volts. Okay. Now, so its value was around, let's write that down. So over here, the linear range which we got over here was how much was that? Let us check that again. So I'll take this cursor, place it over here at the bottom. I take another cursor and take it over here at the start. Okay. So the range over here, let me maximize this. I have to take a little up. Okay, this is also a little bit this side. Yeah. So it's around 2.5777. Let me write over here. So linear range of Opamp in the closed loop configuration is in volts. Okay. Now next, let's check uh, the slope of this. The slope of this will should give us 11, right? So let's test that out. Okay. So we take one value over here and another value we have to take it somewhere else. Let's say we take it over here. Okay. So now let us take a bigger range. Okay, so directly I should divide the difference between the y2 minus y1 upon x2 minus x1. So that will be 15.99 divided by 1.454. So that number is coming out to be 10.99. Okay, so let us write this out also. So my comment text. So here I am writing the slope, which is your closed loop gain ACL, which is given by 10.9972. Okay, that's the number which we are getting over here. We are expected to get 11, but we are getting very nearby 11. And the closed loop gain has drastically reduced from the open loop gain. Open loop gain was 2 into 10 is to 5. It has drastically reduced due to negative feedback. It has come down to 10.99. But at the same time, we have a very large increase in the linear range. That means the chances that this op-amp will be falling in the linear region, it's very, very high. Okay, so that's how we got it in the open loop configuration in a nutshell. The linear range is in volts, which is a drastic improvement. And so Opamp can be worked as a linear in all the linear applications which we have studied. Opamp was working within this range. And also the slope of this transfer curve, which is your closed loop gain. Actually, I have written wrongly over here. This should be a closed loop gain ACL. So that ACL will be 10.9972, which is close to 11. That's what we get. Okay. So definitely the reduction in the closed loop gain with the negative feedback has resulted in the increase in the linear input range. Okay, so the range of input over which the op-amp works as a linear amplifier is this linear input range, which will be in volts right now if op-amp works in the closed loop configuration. Okay, and what's the advantage of working in the linear region? The output is predictable and proportional to the input. Okay, we know its behavior. So we have founded out the slope of the transition region exactly to be equal to 11, which is much less as compared to 2 into 10 is to 5. And the linear region is 2.6 close to volts, which is very large compared to the microvolts. Okay. Here there is only one mistake. Instead of AOL, I should have written over here ACL, because this is the closed loop gain. Okay, so we have come to the end of this topic. We have seen in today's lecture two topics, that is the transfer curve for open loop configuration and the transfer curve for the op-amp in the closed loop configuration. So that's it for today's lecture. Next time we'll look into the frequency response of op-amp in open loop and closed loop configuration. So until then, have a good day and thank you.